This one, we will be looking at the difference between means when the population standard deviation is unknown. And what this means is that we will be doing a t-test rather than a z. When we knew the standard deviations of the population, we could do a z-test. Breaks it, and then we had our proportions. This one, though, with the t-test, there are going to be two types of t-tests. And we're going to branch out here. One is while we don't know the standard deviation of the population, what we do know is that the variances of those populations, so variance is squared, that they are equal. Okay, so when variances are of the population, variances of the population are equal, then we will do the pooled t-test. We'll highlight that a little bit more. Pooled t-test, when they are not known or there's no comment about that they are equal, then we do a regular t-test. Okay, so pooled versus regular. So we'll see how that all works as we move forward. Okay, t-tests. So the difference between means, what we need to be able to do a t-test is that we have two samples and we use it to find the difference between two population means. Again, we're working with the sample means, but we're trying to find the population means, if there is a difference or whether they're the same. For using the t-test, we do not know the population standard deviations, so we will be using the sample standard deviations. Both samples need to be randomly generated or chosen as random samples. They also need to be independent samples. As we saw earlier, if they're dependent, there's a special way to handle those. So these would be independent for the t-test. And the populations need to be either normally distributed, that will usually be commented on in the question, or both sample sizes need to be greater than 30. Okay, so here's the routing of things. Are both population standard deviations known? Well, that's what we did in the last one. We would use, if that's the case, in the second case, and the populations are normal, sample size at least 30, then we would use a z-test. Okay, so that's what we did last time. If not, we can't, right? If they're not normal or sample size at least 30, then you cannot run a z or a t-test. So what we're looking at in this section, we ask that same question. Are both populations normal, or are both samples at least 30? If we get a yes there, then we branch out. We have to check the population variances. If they are equal, we do the pooled t-test. If they're not, or we don't know the population variances, then we do just a regular t-test. And where you'll see that difference is when you come into the calculator, we go to inferences, we're going to go to tests, we're doing two means, and notice we have either the t-test or the pooled t-test. So the difference, you're going to always have to do this check. Do we know that the population variances are equal? If yes, that's when we will use the pooled t-test. If not, we use a regular t-test. Formulas inside these are slightly different, as you will be able to see later in this slide deck. However, we're just going to let the formulas be built in. We will be using it. So as long as we make the right choice for pooled t-test. So if you're getting a wrong answer, you might back up and see, oh, was I supposed to do a pooled and I'm doing a regular, or am I doing a pooled when I'm supposed to do a regular? So if we're doing the wrong one, you can kind of see the way the calculations are made are different. Okay. So let's keep moving forward then. So let's look at our first example going through this. So first of all, we'll decide whether we can use the t-test. This is the results of a state mathematics test for random samples of students taught by two different teachers. The same school are shown below. Can you conclude that there is a difference in the mean test scores for the students of the two teachers? We're asked to use a 10%, 0.10. We're told to assume the populations are normally distributed. So, okay, we can do this. And then we're also told the population variances are not equal. So we will not be doing a pool test. They're not equal, so we do a regular t-test. Put that in there. And so let's go ahead and walk through this. All we have to do is get the right information plugged into the right place. First of all, the null hypothesis is always that the difference is equal to 0. Always. We come down here, can you conclude that there is a difference? This is the word for not equal. If they said less than, we would use less than. If they said greater than, we would use greater than. Okay, so this is where we can have these choices. And since they're just looking, are they different? That means that they're not equal. So we go for this two-tailed test. So that's an important part. Otherwise, how it sets up the rejection regions and everything will be different. Okay. So we're going to input our statistics rather than put in a data set. We've got the mean of sample 1 is 473. So we enter that. The standard deviation of sample 1 is 39.7. Enter that. Oops. And then the sample size was 8. Now the sample sizes are both below 30, but since the populations are normally distributed, we are okay to do what we're doing. Mean of teacher number 2, the mean score was 459. The standard deviation of 24.5. And a sample size of 18. So it's going to, the formulas take into effect all the variation, the sample sizes, and all that kind of stuff. We want it at an alpha of 10%. The default is 5, so we change this to 0.1. We're good. And now we've run the tests. We got a t-value. We've got a p-value. And at this place, we could actually make our decision. We'll also see a visual way to do it. But we're taking this alpha level of 10%, and we're comparing it to the p-value of 37.9%. And what we see is that p is bigger than alpha. So that is a fail to reject. Fail to reject what? The null hypothesis. So we can't say they're equal. We can't say they're not equal. We do not have enough evidence to reject. We do not have enough evidence to say there is a difference. Okay, and what you can see in the next screen, if we go to the next, we see the rejection region with the I don't know, the zebra stripes, let's call it that. That's the rejection region, and the golden color, the yellow, gold, whatever you want to call it, the p-value is not contained in that rejection region. It's way in here. So it's more into it could be in the normal. Now again, you see with this p-value, it could be way out here, but it also could be in here. So we just don't have enough evidence at this point. Fail to reject. One of the things that could have happened, we could have got a larger sample, but maybe that was the class size, right? So anyway, we fail to reject. We're not in the rejection region. And that's how we run this t-test. The next example we're going to take a look at is as you can maybe guess it, will be a pooled t-test. I'm going to back it up. And I just know that because since we have two that we could do and we're only having two um, examples, that's what's going to happen. An automobile manufacturer claims that the mean driving cost per mile of its sedans is less than, so look for that word, that's going to help us set up the null hypothesis, less than that of its leading competitor. You conduct a study using 30 randomly selected sedans from the manufacturer, 32 from the leading competitor. The results are shown down here. And then we're told the significance level at the alpha equals 5%. Can you support the manufacturer's claim? Assume the population variances are equal. So this is a big deal right here. Population variances are equal, That tells us to do a pool t-test. So we go into the pool t-test and you'll see the inputs are going to be pretty much identical to what we do to a regular t-test, but the formulas behind them are different, so we'll end up with different answers. In the null hypothesis, always equal to 0. Leave that. But the alternative, in this case, it's not just different, it's less than. So we're going to come in here, we're going to choose the less than option. Okay. And the manufacturer and the competitor. The manufacturer is 1, the competitor is 2. Let's see how we end up. Input our statistics. The mean for the manufacturer is 0.52, 52 cents per mile. Standard deviation is 5 cents per mile. Sample size is 30. For the competitor, the cost is 55 cents per mile. And standard deviation, 7 cents per mile. And 32 sample size. Alpha is equal to 0.05, 5%. That's what the default is, so we'll leave it alone. We've got our values here, and now we can actually look at our p-value compared to the alpha value. So alpha is 5%, p is 0.029, so 2.9%. This is smaller. P is smaller than alpha, so for this case we can reject the null, which is that they're equal, and then we have evidence. I'm really backwards today. We have evidence. We have enough evidence. At this significance level to support the claim. And the claim support that its cost per mile is less than. Okay. And again, it's always good to come down and see the visual. We're down in the left tail test, and we can zoom in here a little bit, and we see that our p-value, our probability, is completely contained in the zebra striped rejection region. We definitely reject. So that's the main thing. So we're running these hypothesis tests to make a decision of yes or no, reject or fail to reject. That is what all of this is about. And we have that sufficient evidence. Okay. And if you would like, so that's the lesson for today. You're going to be doing these similar things. Again, remember to check whether the variances are equal or if they're not. That will help you determine whether to do a pool t-test if they are equal or the regular t-test if they're not. After this, if you is here really for your benefit, if you want to see the formulas that are used, you can go through the rest of the slide deck, see how each one plays out. These are all embedded within the calculator. What I want you to get is how to set it up, what data, what statistics you need to input, and then once you've input everything and the calculator has used these formulas to make the calculations, that you can make the decision to either reject or fail to reject, and then explain what those things mean. So actually, what might prove more helpful is once we're done, we do, this is the step by step what you do. We kind of do that. We don't use the tables, we don't use the formulas, they're all embedded. Um, but what you might like here is when you go through the examples, they tell you the fail to reject, and then they give you this nice verbiage of what it means when we fail to reject. There is not enough evidence at the 10% level of significance to support the claim that the mean mathematics test scores for the students of the two teachers are different. Again, it doesn't say they're the same, but it just says we can't say they're different. And certainly these tests do not directly test something um, as it goes. And then if you keep going, you see the other example, and it's been worked out with the formulas, and you see that we reject the null. And when we reject the null, we do have enough evidence at this significance level, at least, to support the manufacturer's claim. Now, if we did a 1%, we would not have had enough. But at the 5% level, we do. Okay, so that's why that's important. Okay, so now's the time to dig in and get into the homework, practice these over and over, and make these hypothesis test decisions.